so with 3.2, we are continuing our discussion or our unit on applications of derivatives. Again, this is just very elementary calculus, with it being calculus 1. So the level of applications we are getting involved with are just, very little. We're just dipping our toes in the water, just kind of getting an idea of what some of the applications are. So section 3.2 is what derivatives tell us. Well, sometimes they'll tell us jokes, sometimes they'll tell us scary stories, just depends what type of mood they're in. Sometimes just won't stop talking. I mean, gosh, shut up, derivative. But every now and then they give us a good nugget of information. So what do derivatives actually tell us? Well, one of the applications of derivatives is using derivatives to find the shape or the behavior of a function. So last class, Friday's class, we had talked about finding absolute max, absolute mins, local max, local mins. And those tell us something about the shape of the graph because it tells us the high points versus the low points. Today, we're going to dive deeper into that to learn more about the behavior, or more specifically, what type of shapes all of our graphs are going to be in. Now, we do have a lot to cover today, so I apologize. I might move a little bit quickly. However, a lot of it involves the same steps that we did to find local maxes and local mins. So it's basically the same process, just a different interpretation of the data. All right, so first we're going to start off with kind of a review, but kind of not. We're going to be finding intervals of increasing and decreasing from graphs. Now, this is something that I'm sure a lot of you folks did in pre-calculus. So again, that's why it's going to be the review part, but then we're going to add in little snippets of calculus to be like, oh, that's why this is called this, or that's why that happens, and things like that. So it's a review, but a review with some calculus words. All right, so before we dive into that, let's just quickly review how we know something is increasing or decreasing. So using our pre-calculus knowledge, or maybe something we have learned in this course, how do we know when a function is increasing? No pressure, my non-honors class knew the answer right away. So, not to shame you or anything, but come on. No, you guys all know this. Come on, use your thinker caps. When is something increasing? When it's...
When f of x is greater than 0.
That just tells us that the y values are positive. That doesn't actually tell us whether or not we're increasing or decreasing. As the x values get higher, well, again, x values being higher just means we're moving further away from the origin. So also not so...
Positive slope.
Positive slope, there it is. We know something is increasing when the slope is positive. Yes, got it. Kind of sort of not really redeemed yourself, but I'll take it. No, really, I could tell you anything I wanted about my non-honors calculus class, and you'd have to believe me because none of you are in it. And I could be lying the whole time just to elicit a response from you. But, I never lie, ever. All right, so if the slope is positive, that's our pre-calculus thing, right? I mean, slope, pre-calculus. I mean, come on, we're in calculus now. What does slope mean in calculus? Slope is the...
Derivative.
It is the derivative. So we know a function is increasing when the derivative is positive, or when f prime of x is greater than 0. Look at us, geniuses. I mean, one could say you folks are geniuses because you signed up for the 9:30 calculus class, not the 8 a.m. calculus class. So, it works on lots of levels. All right. So then if a function is decreasing, how do we know a function is decreasing?
If the slope is negative.
The slope is negative. And then what does that mean in calculus words?
The derivative is negative.
With enthusiasm. The derivative is negative. All right, so f prime of x is then less than 0. I wish I had that much enthusiasm. All right, am I good to move on? Good, because I'm not waiting. All right, so intervals of increasing and decreasing are based around critical points. So we kind of witnessed that last Friday in class, when in order to find local maxes and local mins, we first had to find the critical points. We had to determine whether the intervals were increasing or decreasing, and then we could use that information to determine if the critical points were in fact local maxes and mins. So we've kind of already talked about the fact that intervals of increasing and decreasing are based around critical points. All right. What's a critical point? Or when does a critical point happen?
When there's a turning point in the graph, or it's hard to explain.
Well, I agree with the turning point in the graph. That didn't seem that hard. There's another one.
When the function, when the derivative is undefined or it equals 0.
Those are two other things I'm going for, which is correct. The turning point is when the derivative is equal to 0.
Oh, yeah.
When do we have a derivative that's undefined? What characteristic do we have on the graph?
There's a vertical tangent line.
That's true. I guess not what I'm looking for, though, so I'm not asking the right question. So where does a vertical tangent line happen? Cusp. Right. So we know that we have critical points at corners or cusps. And that is when the derivative is undefined. With my wonderful handwriting right there. All right, and then there's one more place where we have a critical point, or there's another place where the derivative is equal to 0. I don't think we actually gave this a name, but I'm going to call it a pause in the graph. And we'll kind of dive into that in a moment. And a pause in the graph is when we also have the derivative equal to 0, or we have a horizontal tangent line. All right, so looking at this beautiful graph right here, we can see that at point A, we have a vertical tangent line, which means obviously it looks like we have a cusp. So therefore, we could say that at f prime, or we can say f prime of A is undefined, because again, vertical tangent line. Then if we look at point B at x equals b, hopefully we see that there is a horizontal tangent line there, which means f prime of v is going to be equal to 0, because horizontal tangent line has a slope of 0. At x equals d, we can see there's another turning point here, which means that there is a, where is it? Come out and play. There it is. Another horizontal tangent line, which means f prime of d is equal to 0. But there's a third spot that is a critical point, or a third spot that has a horizontal tangent line. And that is right here at C. And this is what I was talking about, a pause in the graph, because we can see that going from B to C, we are increasing. Then we kind of stop and we take a break, like we climbed to the mountain, we ran out of breath, and then we started climbing again, going up. So this point at x equals c is what I'm going to call the pause. And there is a critical point there, but there is no local max or local min. So we can see that these 4 points are critical numbers, and they split our graph up into these different intervals. So now we just need to figure out if it's increasing or decreasing. So in this first section here, we can see that hopefully that this part of the function is increasing. Hopefully we can see between a and b, our function is decreasing. And then going from b to c, hopefully we can see our function is increasing. And then going from C to D, our function is also increasing because we just took a little bit of a break. And then going from D to infinity, our function is decreasing. All right, any questions so far? Super tough, I know. All right, so if function's increasing, what do we know about the derivative? Derivative is positive. Yes, best student ever. The derivative is positive. So therefore, we know f prime of x is greater than 0. When the function is decreasing, what do we know about the derivative? It's negative. Man, you're on a roll. So f prime of x is less than 0. And then increasing, greater than 0, decreasing, less than 0. And then you guys should be very thankful to have that particular student in your class. All right, so next and final thing we're going to do on this slide is we're going to actually identify the intervals of when our function is increasing versus when it's decreasing. All right, so don't copy this down yet. I might be making a mistake. Just throwing it out there. Intervals of increasing. I can see that I'm increasing from negative infinity to a. I guess you could write that one down. That one's good. And then I could say, don't write this one down. I can say that I'm increasing from b to d, right? And if you agree that that's right, you weren't listening to me at all because I said this is wrong. Why can I not say that we are increasing from b to d?
There's a pause at C.
Exactly. Because in calculus, we are defining a function being increasing when the derivative is greater than 0. At x equals c, we see the derivative is equal to 0, which means it is not greater than 0, which means it is not increasing at that particular point. So therefore, I have to break this up to be from b to c and then from c to d. We cannot include x equals c as increasing because it's not. There is a pause. Decreasing, we don't have that problem. We can go from a to b and then from d to infinity. Ooh. Calculisified. Calcified? Fied de calculus. A little bit of French. I don't speak French, so if anybody speaks French, I'm sorry for insulting that language. I actually took 2 years of French in high school. I can say je m'appelle, Kuhlman, and I can say como está. No, that's not French, is it?
That's Spanish.
That's Spanish. All right, well, I took 1 year of Spanish too. And there we go. That's the extent of my foreign language. I can't be any more of a white American than that right there. I have nailed the ignorance of my entire, yes, classification of human beings. I am a disappointment to society. All right, now that I have shamed myself, can I move on? Great. All right, so given the graph now, we are going to go through, we just want to find out where the derivative is less than 0. Actually, I guess I'm thinking about it more. I guess I'm not a disgrace to white male Americans because I think white male Americans are proud of who they are, even though they shouldn't be because we are ignorant. Sorry, going down a rabbit hole there. Anyways, white males, we're the best. We're also all the problems in the world. All right, so in order to find where a derivative is less than 0, remember, that means we want to figure out when the function is decreasing. And based on our last slide, we know that in order to figure out where a function is decreasing, we first have to start with our critical points. And we know our critical points exist where we are going to have turning points, corners and cuspes, or pauses. So turning points, corners or cusps, or if we have any pauses. So in our graph, I can see that I have a turning point right here, and I can see that I have a turning point right there. And now I'm just going to estimate what these values are. These are not precise, but I'm going to say our first turning point happens at x equals negative 1.5, and this turning point is going to happen at x equals 1. Again, those are just approximate guesses. All right, so I checked for turning points. Does this graph have any corners or cusps? I don't see any, so we're good. We checked for that. Are there any pauses in this graph? Any points where we're out of breath and have to take a break? No. So no pauses either. So great, we've found all of our critical points. And now we just need to identify where the function is increasing versus decreasing. I can see in this first part right here, we are increasing. So this is where f prime of x is greater than 0. This in-between piece is where we are decreasing. So here is where f prime of x is less than 0. And then our final piece right here, we're increasing. So f prime of x is greater than 0. Now, does this seem like a familiar process to anybody? Maybe from like class on Friday? Maybe something that has a specific name? Anybody? Anybody? Bueller? Bueller reference go over most people's heads? Yes, I'm old. It's the first derivative test. Where was my star student there? Sorry, I wasn't paying attention. Oh, gosh, stupid star student. Yes, this is the same process as the first derivative test. So we use the same process we did to find local maxes and mins to also find increasing and decreasing. But anyways, let's finish the problem. All right, so we know that f prime of x is less than 0 over the interval from negative 1.5 to positive 1. Boom. Question answered. All right, can I move on? Great. Uh-oh. Lots of curves on this one. Why don't you try this one on your own? Ooh. All right, maybe if somebody has a solution, if they would like to share, that would be wonderful.
F prime of x is greater than 0 from negative 1.5 to negative 0.5. From 0 to, that would be about 0.5, I guess. And then from 1.5 to infinity, or 2, I guess, 2.
I basically agree. I had estimated different x values for my critical numbers, but since we don't actually give the exact values, I agree with what you had said, except I went to positive infinity at the end there. So I did negative 1.5 to negative 0.75, from 0 to 0.75, and then from 1.5 to infinity. But I would also accept the 2 as well, because that's where the graph, does stop graphing. Yeah, no, great. Any questions here? All right, moving on. So finding intervals of increasing and decreasing algebraically. So like we said on the previous slide, this whole process is the same process as the first derivative test. So we're going to use the first derivative test here, except we're just going to interpret the outcome differently. So we want to find intervals of increasing and decreasing on y is equal to x cubed minus 3x squared minus 9x minus 1. All right, so we are using the first derivative test here to find intervals of increasing and decreasing. So first derivative test says we need to find the critical points first. So to find the critical points, we need to figure out when the derivative is equal to 0 or undefined. So we probably should find the first derivative, first. So y prime is going to be 3x squared minus 6x minus 9. All right, so now we need to figure out when this expression is equal to 0 or when it's undefined. Will 3x squared minus 6x minus 9 ever be undefined? Nope. Wrong. So therefore, we just have to figure out when it equals 0. So we'll set the derivative equal to 0. So 0 equals 3x squared minus 6x minus 9. And now we have a nice simple quadratic formula, or excuse me, quadratic equation. So we can solve that. I guess first I'm going to factor out, actually I'm going to blow it. First factor out of 3, so we get 3 times the quantity x squared minus 6. Man, math, I can't do it. All right, who else wants to teach today? Anybody? Anybody? No? When I taught high school, I was tired one day, and I, of course, asked that. I'm like, oh, I'm tired. Who else wants to teach? And I had like 3 kids raise their hand. So I let them teach. And they actually did a fairly good job. I had to sit in the back and actually pay attention to make sure that they were actually like explaining things correctly, or if they had questions that they would actually ask. But I was actually impressed. They did it. Okay, so I'm not telling you that story to imply that I think you guys should take over from me teaching, because even if you wanted to, with the technology restrictions we have at the moment, I have the iPad, I have the presentations and whatnot, it would kind of be impossible for you to do it. So sorry, I'm not trying to imply you folks should be teaching the class. I didn't want to do that.
Well, what about the people with touchscreen computers?
All right, Caleb, you're up. It's all you. Do it. Actually, he's right. I mean, you could, if you have the touchscreen, you could annotate on it and just tell me when to change slides. So yeah. Caleb, let me know when you want to take over. I'm game. I will say it is more challenging than you think to be as corny as I am with my jokes. So you might need some practice. I'd recommend eating a can of corn the night before, let it digest, sink in overnight. All right, so we do get then x equals 3 and x equals -1, and these are our critical points. So the first derivative test then said that we need to set up an interval and determine where it was increasing and decreasing. So we can set up our interval. We know the domain for our function is -∞ to +∞ since it's a polynomial. And then we can come in here and we can plot our critical points. Then we said we need to pick test values in each one of these intervals to plug into the derivative. So I'm going to pick x equals -2, x equals 0, and x equals 4. Now, we are trying to find when the function is increasing or decreasing, which means we want to find when the derivative is positive or negative. So we're going to plug these test values into the derivative because that's what we're trying to find. Don't confuse this with trying to find absolute extrema where we plug them into the original function. Because with absolute extrema, we wanted to find the y values. All right, so I'm using the table feature in my calculator. What do you say? -2, 0, 4. So f prime of -2 is going to be 15. F prime of 0 is going to be -9. And then f prime of 4 is equal to 15. So therefore, our first interval is increasing. Our second interval is decreasing. And our third interval is increasing. So now we just need to actually identify the intervals. So let's see, we are increasing from -∞ to -1 and from 3 to infinity. And then we are decreasing from -1 to 3. Boom, done. So again, this is very similar to finding local max and local min, because we still had to make this chart. We still had to identify when we are increasing versus decreasing. We then just use that information to find local max and min instead of just stopping at increasing, decreasing. So we're not learning anything new here. We're just interpreting the results differently.